Okay, so we'll review question 4. An ideal fluid of density rho flows through a pipe as shown. The diameter at point 1 is 60 centimeters, and the fluid flows at a speed of 62 centimeters per second. Pressure at point 1 is 1.2 by 10 to the 5. The pressure at point 2 is 1.13 by 10 to the 5. And at point 2 lies 80 centimeters below point 1. The diameter at point 2 is 20. Determine the density of the fluid. Okay, so again, it's another ideal fluid flow or ideal fluid dynamics problem with a lot of different information, some awkward units in the diameters and the speeds. But yeah, so any question with any quantitative question surrounding Bernoulli's equation is typically challenging, just given the vast number of terms. Okay, so let's maybe try to add some of this information to the question. So the diameter up here, so I can start with this particular quantity here. So this is 60 centimeters, the diameter at the water pipe. It's moving here with a speed of v equal to 62 centimeters or 0.62 meters per second. Let me do that conversion. So that's 6. Pressure of 0.1. So that's 1.2 by 10 to the 5 pascals. And then the pressure at 0.2 down here is 1.13 by 10 to the 5 pascals. 0.2 lies, so if I have, what's the best way to draw this? I draw a little arrow here, and here. Let's say that this height difference here is 80 centimeters. Between points 1 and 2, and the diameter of point 2 is 20. So this is the last piece of information. This is 20 centimeters or 0.2 meters. Okay, determine the density of the fluid. Okay, so quite a bit of work in here. Okay, so let's start with, again, writing Bernoulli's equation for this context. So now that P1 plus rho GY1 plus 1/2 rho V1 squared is equal to P2 plus rho GY2 plus 1/2 rho V2 squared. Okay, so we see that we have 4 terms with rho in them. So I want to collect them on one side of the equation and collect the differences in pressure on the other side, and we have the difference in pressure. So I want to basically isolate rho for this problem. So I've got P1 minus P2 equals rho GY2 minus rho GY1 plus, so just basically connecting these terms together, and I have 1/2 rho V2 squared minus 1/2 rho V1 squared. Okay, so sort of collecting the kinetic energy terms and the potential energy terms together, and then I can see I have rho in each of these quantities. So P1 minus P2, I'll take out this rho. I have GY2 minus GY1 plus 1/2 V2 squared minus 1/2 V1 squared. Alright. Okay. Yeah, so where we're at so far. We can make life a little easier if we set one of these y values to 0. So I typically will choose the lower point always to make this equal to y equals 0. So that means that y2 is equal to 0. So that means I can go ahead and cancel out this term over here. So I put negative 3y1 plus 1/2 V2 squared minus 1/2 V1 squared. Okay, so that's negative 3y1 plus 1/2 V2 squared minus 1/2 V1 squared. 1/2 V2 squared minus 1/2 V1 squared. 1/2 V2 squared minus 1/2 V1 squared. So Okay, so we know that y1 is going to be 0.8. We have the differences in the pressure, and we have the speed at 0.1, so the only term we're missing here is the speed at 0.2 in order to basically rearrange our equation. So we do need to think about what is the speed at 0.2. So again, this is going back to continuity. So again, I know that, I'll do some different color. So I know that again, V1 is equal to A2 times V2. And again, we have a nice unit, sort of a nice fraction in the change of the diameter. So you can, of course, you can convert this numerically. I encourage you, if there was a nice easy conversion or easy sort of proportion in the diameters, then to work sort of semi-quantitatively. So we go from a 60 centimeter diameter to a 20 centimeter diameter. So that's a change by a factor of 3 in the diameter, which means that the area will go down by a factor of 9. The area goes to the factor of diameter squared, which means the speed at 0.2 has to be 9 times the speed at 1. So area 2 is 1/9 the 9 of area 1 due to the having 1/3 of the diameter. So V2 is equal to 9 times V1. Again, you can put that in there if you know, in a sense, do 9 times V1 and square all of that. The V2 works out to be, you can also just do it numerically. It's to be 5.6 meters per second. 9 times 0.6 should be roughly around 5.6. And yeah, so I think we have everything now to basically rearrange this equation for rho. So I have rho will be equal to P1 minus P2 on the top, all divided by this negative GY1 plus 1/2 rho, 1/2 V2 squared minus 1/2 P1 squared. And if you wanted to take out the halves, again, you can do that here also, make things a little easier for yourself also. Okay, I believe, as I said, you have P1 will be equal to 1.2 by 10 to the 5, and P2 is 1.13 by 10 to the 5. G is a constant, Y1 will be 0.8 meters, and the V2 will be this 5.6 all to be squared. V1 is the 0.62 all to be squared. So your unit conversions is that Y1 is 0.8 meters. That's the only unit conversion. Since I converted the 0.62 earlier in the problem, that's the only other conversion factor you want to be careful of. That V2 and V1 are in meters per second. The pressures are in pascals. So if you put in those numbers, and you should end up with the rho is something less than water. So 930 kilograms per meter cubed. So choice E. It's pretty challenging for any question, lots of things to consider from transferring from the text to the figure. Some unit conversions in the heights, in the speeds, and then thinking about the continuity expressions to make sure you have the right speeds at each point, and then a good bit of algebra to think of rearranging for rho. So overall, a pretty challenging question.